Let's get started. Can people hear me with this mask on and this mic set up? We're good? All right, good. The lecture today starts the scientific background about the climate problem, and we're going to be talking about this for several lectures in a row now. And the first piece of it is the sort of the way in which the greenhouse effect works, because it's important to understand how much of this stuff is completely settled science and what part of it is not completely settled. And this part of it is completely settled, but I guarantee you, if I asked, I think probably everyone how this works in the class, I'd get a wrong answer. And the answer would be something like, it's like a blanket that bounces heat back from the atmosphere to the Earth. And that's sort of right, but it misses the essence of the way in which the thing works. So the first thing I'd like to do is to talk about that. But before I even do that, I want to talk about some definitions. And it's really worthwhile to read through these definitions so you have some idea of the units, because we're going to be talking about units all the time in here. Indeed, when you read stuff about what the Biden administration and Congress are proposing in the latest bills, it's all about how many gigawatts of electricity and stuff like that. And the question is, what are those things? Well, a watt is roughly the force of an apple falling on the Earth. Okay, that's what it is. If you're to use the Newtonian metaphor, the force of an apple falling from sort of the average height of an apple tree, 3 meters up, and hitting the ground, that's about a watt. Okay, it's technically 1 joule per second, but blah, blah, blah. A kilowatt is 1,000. Whoa. We're going to see if that continues. Is 1,000 of those, and a megawatt. We're good? Okay, we're good. And a megawatt is 1,000 kilowatts. A kilowatt, if somebody's talking about a kilowatt, that's roughly a horsepower. It's 1.3 horsepower. So it's 1 1/3 horsepower. So when somebody's talking about 1,000 kilowatts, which is a megawatt, that's 1,300 horsepower. And if you're talking about a gigawatt, that's 1.3 million horsepower. That's what it is. People have an idea of what horsepower is. And so a really super powerful supercar has got about a megawatt in it now. But nobody on campus has one. And if you do, you should be ashamed of yourself. I'll put it that way. Because you can buy a Tesla that's faster. All right. Pre-industrial, no, that's not, no more of those things. Pre-industrial CO2, that is before humans, was about 280 parts per million. And remember that a part per million is a teeny weeny little number. 1,000 parts per million would be 1 part in 1,000, which is 0.1%. So our current concentration today, which is something like 417, is 0.0417%. Tiny amount in the atmosphere with a big impact. The term radiative forcing means a net change in the radiant energy hitting the Earth's surface. So how many photons and what's the average energy of those photons, as heat containing packets of energy, how many quanta of energy, radiant energy, are hitting the surface per unit time. And remember that radiant heat energy comes out of everything. When you look at a piece of iron that's been heated up in a forge and is glowing red hot, it's because it's radiating light at a temperature, at a wavelength corresponding to its temperature. As it cools, it becomes duller and duller and duller. And once it's no longer glowing even dark red, it's still got a color, you just can't see it. all right? And you, all of us here, are radiating this infrared energy. And so we're all like light bulbs in here, about 100 watts of it per person. So radiative forcing is a change in that radiant energy, visible light, infrared light, all that kind of stuff, hitting the Earth's surface. Climate sensitivity is the amount of warming we expect on or near the planet's surface from a doubling of pre-industrial CO2. So when somebody talks about a climate sensitivity, that's what it means. If we go from 280 to 560, double the pre-industrial, how much change does that correspond to in terms of radiative forcing? If the radiative forcing is in fact what's driving the temperature change. And that's about 3.7 watts per square meter of radiative forcing. So the amount of stuff we're talking about here is not trivial. A couple or 2 or 3 watts per square meter of radiative forcing is about 1% of the energy budget of the Earth, a little bit more. But that still corresponds to sticking one of those little Italian lights like they put on Christmas trees on every square meter of the planet's surface. And if you ask yourself, if we did that in here, would it heat the place up? Well, probably a little bit, right? Certainly if you put a 10-watt bulb every square meter, it'd be hotter than blazes in here. It'd probably cook us, okay? So it's enough to make an impact. And a climate feedback is a process that either amplifies or reduces the climate change caused by radiative forcing. If it amplifies it, it's called positive feedback. It's like a runaway reaction. If it dampens it down, it's called negative feedback, and it reduces the impact. Okay, so how does radiative forcing work? Well, prior to the pre-industrial and after the ice ages caused by orbital variations in the planet's orbit about the sun and the way in which it wobbles on its axis and blah, blah, blah. There's a lot of stuff there that's known well that causes the ice ages. But since the last ice age, the radiative forcing and its distribution across the planet's surface has been about the same. And that's signified by this steady arrow coming in. And so what happens is the Earth's temperature and distribution of temperatures come into equilibrium with that constant radiative forcing, which heats up the Earth. In the same way that I don't know if you have ever been in a house that has radiant heat in the floors. You pump like water or sometimes have induction coils in the floors, and they actually broadcast infrared radiation that hits you and warms up your skin, okay? So this incoming solar radiation is like an infrared heater for the Earth. It warms everything up, or it's it can be visible radiation too. And then eventually, as the Earth's temperature goes up, it glows more and more brightly, right? The same way that you're glowing, we just can't see it. And the outgoing radiation has to balance the incoming. Or the temperature would just keep going up and up and up and up if incoming is greater than outgoing, or keep going down and down and down and down if the reverse is true. So it was in balance, has to be in balance over these long periods with relatively constant radiative forcing. Aside from really minor impacts, like the radioactive decay of materials in the Earth's crust, all right, which are kind of held over from the previous star that supernovaed here about 6 billion years ago. Okay, so you can think about this with an analogy of the Earth being a store, and customers are walking into the department store, 1 per minute, and each person stays 2 hours loitering around in the store until they leave. And so there's 120 people in the store because 2 arrive every minute, stay for an hour, and then leave an hour later. And so there's 60 minutes in an hour, and so there's 120 people in the store, even though 2 are always coming in every minute and 2 are always leaving every minute. Okay? Now, what happens is that somebody adds to the greenhouse gases around in the atmosphere. And those greenhouse gases intercept outgoing long wavelength infrared radiation and absorb it in the molecular structure of the CO2 molecules and some other greenhouse gases, and then release it in all directions. Some of it continues upward along its way, and some of it goes back down to the Earth's surface for another stay. Where it gets absorbed by a leaf, and then and eventually the leaf cools off, and so on, right? So stuff happens. Even longer, it could be absorbed by photosynthesis, put into biomass, which then has to decompose, blah, 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 but it eventually gets out again. But the important point is that the greenhouse gases cause quanta of energy that are coming in all of a sudden to start loitering near the surface of the planet. And this is kind of like somebody unveils the new iPhone, and you've read reviews, and someone says, don't buy the thing, it stinks, and others say, oh, it's really pretty good, and you want to find out. So there's a new iPhone, you get to use it, all right? And for free when you're leaving the store. So you pick it up and you walk around, and that causes you to spend an hour extra in the store. So now all of a sudden, every person in the store starts all at once spending 3 hours in the store. And so for the next hour, nobody leaves, and the number of people in the store increases by 1 per minute, right? Relative to what it was before. And it reaches 180 1 hour after the first phone appears, okay? And so that's like, phone zombies walking around the planet, okay? And so that's all that's going on here. Because the greenhouse gases cause quanta of energy to loiter longer near the surface, there are more of them near the surface than there would be without the greenhouse gases. And it's this loitering of energy that actually causes the climate to warm. Eventually, what will happen, if you stop changing the greenhouse gases in the atmosphere, the Earth will heat up, glow more and more brightly, and reestablish a new equilibrium, okay? Where it'll now have a higher temperature, but the temperature won't be increasing anymore. And that's the purpose of the net zero emissions initiatives that are all over the place, to freeze the atmospheric CO2 level so that it stops rising. Now, we'll learn that it does a little bit better than that, but that's the way you should think about it. This is going to freeze the atmospheric CO2 level, causing us to re-equilibrate with now the same radiative forcing we've always had from the sun, but the longer loitering time of the quanta of energy that are coming into our planet's surface from the sun. So incidentally, I was teaching this course one time, and I got this phone call, and the quarterback, Tom Brady's wife, Giselle Bundchen, who I guess is a model, I don't know anything about these things, was on location with the director James Cameron, the guy who did Titanic, and I don't know what else he did. And they were having an argument about the way the greenhouse effect worked, if you can believe it, okay? And the important point is that Giselle was right and Cameron was wrong. So if you didn't know that, you're in good company, I guess, in the sense that James Cameron allegedly made good movies. Okay. All right, so where are we? So we've got CO2 as the dominant greenhouse gas in the atmosphere. And this is a graph from 2011. We'll be talking about this more. But the extra CO2 that we've put in the surface, in the atmosphere, the increase in the CO2 in the atmosphere since 2011 has caused the radiative forcing of this surface to increase by about 1.7 watts per square meter, okay? The second most important greenhouse gas is methane, and the direct impact of methane has been about 0.6 watts per square meter. And then there's an indirect effect of methane that we could talk about that's not that complicated, but it causes other greenhouse gases to be produced. And so collectively, they're at about 0.95, okay? So those are the two most important greenhouse gases, and their changes relative to 1750 have added that many watts per square meter, because those watts are like loitering around and hitting us multiple times, okay? They like hit us, re-radiate, try to leave, get intercepted, get bounced back to Earth, hit us again, right? And it's all that loitering that has caused it. 1 kilogram of methane, this is just like incidentally. 1 kilogram of methane has 120 times the radiative forcing of CO2. So kilogram for kilogram, it's way, way, way worse. But the residence time of methane in the atmosphere is only 10 years about. It's actually, if you're an engineer, the E-folding residence time, the average time is actually 12 years. Instead of 100 to 1,000 for CO2. Now, why is this important? Well, if I have a source, say of, 10 million tons of methane every year, what'll happen is that source will cause methane concentrations in the atmosphere to rise. And if the average time is 12 years, say it's approximately 10, it's 12 years, that'll eventually result in the concentration of methane in the atmosphere rising to 120 million tons of extra methane in the atmosphere, okay? 12 times the 10 per year, because they stay on average for 12 years. But it'll then stop. It'll stop because 1/12 of the methane is removed every year. So 1/12 of 120 tons is 10 tons, which is the amount that's being added every year. So you see it equilibrates. You add 10 tons a year, it builds up, builds up, builds up slowly, and then reaches 120, at which point the outcoming equals the incoming. The outgoing equals the incoming, and it stops. So if we then cut that methane emission, the concentration falls again. And the global warming, the radiative forcing it produces goes down because of the short lifetime, you see? Whereas for CO2, it just keeps going up and up and up and up. We don't live long enough, all right? Because it lasts, 100 to 1,000 years in the atmosphere. We'll learn more about this. It's complicated, but there's a whole continuum of scales. But a lot of it lasts for thousands of years in the atmosphere. And so if we increase the amount of CO2 in the atmosphere by 10 megatons, next year, to a first approximation, there's 20, and the next year there's 30, and the next year there's 40, and the next year there's 50 added from that increase. And it just keeps going up and up and up and up and up. For the rest of your life, it goes up and up and up and up. And if you cut it back to zero, the concentration doesn't fall. It just stays where you stopped it, okay? So although methane is much more radiatively active, its short half-life means in a real sense that it is much easier to control because it's reversible over human lifetimes, right? In 36 years, an eliminated methane source is going to scrub itself. 95% of the damage it's done to the atmosphere is going to scrub itself away, okay? Now, this is policy relevant today. So today, the news outlets are reporting that, I guess, Biden and Boris Johnson and the EU are agreeing to cut methane emissions by 30% by 2030. And that'll have a direct and tangible impact on the amount of methane in the atmosphere and reduce global warming in your lifetime. There's also all this talk about reducing CO2 emissions. And, Joe Manchin right now is huddled, and is he going to keep the United States from increasing its fraction of renewables in the power sector or not, and make it go more slowly? And environmentalists are all up in arms. And the reason they're up in arms is that every time we delay, the stuff that goes into the atmosphere just stays there and makes it worse for our kids and their kids and their kids' kids and on and on and on and on, right? Unless we go back and formally and deliberately somehow remove it from the atmosphere, okay? So methane and CO2 are really different kinds of problems. One is acute. Every little bit is a gigantically warming, 120 times more, but reversible in some sort of reassuring way. The other is much less potent, but it's inexorable. And you can't reverse anything. Every time you do damage, it's like permanently there for you forever. They represent really different ethical dilemmas as a result, really different economic dilemmas as a result. These two things are fundamentally different, all right? And they're treated mostly in the press and even in policy circles as though they ought to be interconvertible. My own view is that all ways to interconvert them are flawed, and we ought to have separate standards, right? One standard for the long-lived, one for the short, but more on that later. Okay, so if we total up all the greenhouse gases, there are more than just methane and CO2. There's a thing called N2O, which is released from fertilizer, and it's also long-lived, like CO2. And then there's a bunch of really short-lived ones. And altogether, this is the figure that you'll see in the press all over the place if you actually look, if you Google this and that sort of thing. And this comes from, we're going to talk a lot about the Ipcc. The Ipcc is the Intergovernmental Panel on Climate Change. It's a body that was formed by a big international treaty. It doesn't do any new science, but every few years it reviews the existing science. Then it goes into a political morass where governments then criticize everything and try to get political stuff stuck in there. And scientists somewhat successfully rebuff those, but it's just a morass, and this thing comes out every once in a while, and then it's viewed as like the holy scriptures by media types. And so this is the one that you see because it's from the AR5, which is something that, well, started to come out in the early 20-teens, and then the last part of the AR5 came out in, I think, 2016. But the first part of the AR6 came out just a couple of months ago. And so we'll talk about what the AR6 says in a minute, but this is the AR5. And it says that we're currently at 3.2 watts per square meter from all sources. But an aerosol is a particle, a physical particle, not a molecule, but a macroscopic particle, maybe microscopic, but it's lots and lots of atoms. It's like a gajillion atoms, but little, suspended in the air. So dust blowing around in the stratosphere is an aerosol. The smoky particles that you see from the forest fires this summer in the air are aerosols. And we have all these aerosols in the atmosphere, mostly from burning stuff. And the aerosols are cooling agents because they intercept sunlight, don't let it get to the Earth's surface. And so we think the aerosols have 0.9 watts per square meter of cooling, which means the net radiative forcing from these two sources, according to the AR5, was about 2.3, okay? And that's where we are on net. This is important because one of the things that happens when you get rid of coal plants is that you reduce greenhouse gas emissions over the long term, but over the short term, you actually reduce aerosols in the atmosphere, which were cooling the planet, so that it's actually warming over the short term. Nobody really debates this with coal plants because the aerosols also actively kill people, which is like right now, which is considered a more serious ethical problem than causing global warming. So, but there it is, right? So closing coal plants actually has warming and cooling effects. And the warming effects are immediate, and the cooling effects are long-term, right? And the AR6 update is shown here, right? And they now say it's not 2.3, it's 2.71. And the increase in 0.43 watts per square meter is due to an increase in the greenhouse gas concentration since. So 3/4 of the change is due to an increase in the greenhouse gas concentration, and the rest of the change is due to a change in scientific understanding, which means that we didn't understand the full radiative forcing of all these molecules, but at the 1/10th level, right? Little second decimal place, right? So that's where we are now. The current radiative forcing, according to the AR6, which will soon be scripture within all the media, is 2.7 watts per square meter for the net. Now, let's do a little quiz. It's not really a quiz. Well, it's sort of a quiz, but it's a quiz for which there is no penalty for getting the wrong answer. It's a quiz. It's like the perfect, it's everybody's a winner again kind of quiz where all you have to do is participate. So this is the question: because of the effect of aerosols, how much of the observed warming, which we've all observed, do you think is caused by anthropogenic greenhouse gases? 10%, 50%, more than 100%, not enough to answer. And so, vote. Yeah. What do I have to push? The green button? Okay, that's good. Okay, everybody, so click your button as fast as you can because the results are clear. Results are in. What I was looking for is, there you go, more than 100%. Okay? And the reason is that the reason is that there's been a cooling effect that's been saving us from some of the direct effects of the radiative forcing. Okay? So it was a trick question, and it was designed just to make sure to reinforce to everyone that the warming that we've seen is less in some sense than it should have been just from the direct greenhouse effect. And it's because the greenhouse effect has been masked by the aerosol forcing, which has been cooling. Okay, so if we look over the entire Earth, one of the things that I get a lot of crank email, okay, and where somebody has like discovered that all of the science in X is wrong, and he or she has discovered the right science, and they want to convince me of it, and it goes on and on like that. And one of the things that I constantly get is, frequently get, I shouldn't say constantly, but multiple times a year, is that, this warming, how do we know it's not due to just all the people on the Earth's surface and all the warmth they make, or all of the stuff we burn on the Earth's surface, and all that heat energy, and we can't possibly know, blah, 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 right, like that. And the answer is that yes, we can, and all human energy usage is about 0.25 watts per square meter. And we're talking about greenhouse forcing of 3 to 4 watts per square meter out of a total of 240 watts per square meter. So as I said, this number is a couple of percent, 1 to 2% of the total budget. Not a lot, but it's 1 to 2%. It's also useful to think about 1 to 2% relative to what? Well, what would be the temperature of the Earth's surface if there were no sun? And the answer is, that's what it's being heated up against, right? The background of the cold of space. And the answer is very close to absolute zero. And so it's been warmed by all that incoming radiation by about close to 270 degrees Kelvin, okay? A lot. So 1% of that is what we're talking about, which is a couple degrees. And a couple of degrees, 4 degrees, is enough to put alligators in Lake Carnegie, okay? So the point is that from our human scales here, 1 to 2% is actually a big deal for us, okay? And it's because it's 1 to 2% of a big number. But human energy usage is way down the list, 2 orders of magnitude smaller, all right? So it's not human energy, and human body heat is way smaller than that, all right? So it's not energy use, and it's not human body heat. It's greenhouse gases in the atmosphere. And in fact, we can measure a lot of this stuff. For a long time, scientists have put instruments in space to measure the outgoing radiation from the Earth. And it's because you know the radiation, and of course you monitor the sun too. So you know how much is coming in from the sun. And remember, if their imbalance is right, it means that the radiation from the sun stays the same. The greenhouse gases cause the molecules to loiter like people in the store where nobody's leaving for an hour. And so all of a sudden the outgoing radiation goes down, okay? It's not that the incoming radiation goes up, it's the outgoing radiation goes down because the molecules are newly loitering, right? And so you can actually measure that now. And the first measurement in a fancy scientific publication of the imbalance, the current imbalance, is 0.6. It's not as big as the total radiative forcing, of course, because the Earth is trying to equilibrate to the new situation. It's not like the one I said before where, you know, the iPhone is there and everybody starts using it. It's like you're gradually doling out the iPhones or something like that, and so the people can equilibrate as they build up. And so the current imbalance is about 0.6, where the amount coming in, which has been constant, is bigger than the amount going out by about 0.6 watts per square meter, which is 24 times human energy usage, right? So it's a lot. So there's just, in fact, been a new calculation like this released. And you can measure where that heat is in the Earth. And the simplest way to do it is by sticking thermometers in the ocean and lowering them all the way down and doing lots of them, and we do that. And that's because almost all of it's in the oceans. See the upper ocean and the deep ocean there? And the rest is where all the rest of it is, in the atmosphere and in the land. And it's because the oceans are so good at containing heat, high specific heat of water. Almost all of it's in the oceans. So all you have to do is measure the oceans, and you can see the amount of heat building up in there, all right? So that's what's going on here. And you really know this is true, right? These are uncertainties, right? Those bars there. Let's see. Yeah, these bars are uncertainties about the heat content of the oceans. We've known this for a long time. 10 years ago, this was known to an almost certainty, and it's known even more now, right? We really know this. And sometimes another crank thing I get is that sunspots are causing it, okay? The sunspots are causing it. And for a while on the contrarian websites, it was the sunspots are causing it, and that's because there was also global warming on Mars and Jupiter and a whole bunch of other planets, and Mars was going into its seasonal winter, and it was, I was like, oh my God. All right, and so it's like, you don't measure the sun? I mean, what are we doing here? It's like we never thought to actually measure the sun. Of course you measure the sun. All the time you measure the sun. And the irradiance in the sun changes, and it's this really interesting oscillation that's caused by the internal dynamics of the fusion engine in the sun. Really interesting stuff. And the variation is teeny. It's 0.2 watts per square meter, right? And we know that there's this period. So it's not sunspots. It's not solar inputs. It's just not, okay? And it's like saying that it is, it's like the wrong argument, okay? Because it's an argument. In a court of law, you'll just lose with that argument. All right. Now, I'm going to warn you that I'm not going to finish all of today's lecture. And when I don't finish, I'm just going to spill it over and start it up again. So when you download the next lecture, I'm going to be starting on this one, like that. And I'll make it all right in the end. So I want to talk about positive and negative climate feedbacks, because this is really where the game comes in. I think I said in the first lecture that I've worked on a lot of environmental problems, and mostly when I jump into a new problem, I discover that it's less dire than I've been led to believe. And that's because advocates are kind of hyping it a little bit, and with good reason. It's concerning, and this is a strategy. But if you look at the science, a lot of the uncertainties may make it maybe a little less dire than you thought it was. Global warming's the reverse. It's like the more you know about it, the more freaked out you get. There's no more freaked out group of people than climate modelers who actually worry about how to predict the climate system in all its dimensions. And it's because of the presence of positive climate feedbacks that we don't fully understand. All right, that's what makes you freaked out. You know, Venus used to have liquid water on the surface of the planet. Not very long ago, it turns out. It's like shocking. This is not like billions of years ago. This is like just a little bit ago. And got into a positive climate feedback. And now you can melt lead on the surface. All right? And that's not going to happen here, we don't think. But if you said, are you 100% sure? It's like, well, I don't know. Okay, so a positive feedback, an increase in temperature changes something, which further increases the temperature. And that is, of course, dangerous, because it's a self-reinforcing thing. Negative feedback, an increase in temperature, changes something, which acts to decrease temperature, causes it to slow down, and that's dampening, all right? So it's the positive feedbacks that we worry about. So what are the climate feedbacks that are strongest that we fully understand? Well, the direct effect of the radiative forcing is about 0.3 degrees Celsius of warming per watt per square meter of radiative forcing. That's the climate sensitivity. We'll talk about that in a minute, but just right now, take that as a message. For each watt per square meter, we expect about 1/3 of a degree of warming, okay? We'll talk more about that in just a second, but take that as gospel right now. Now, there's a thing called the water vapor feedback. It turns out water vapor is a pretty considerable greenhouse gas. And so global warming, which heats up the surface, evaporates more water, and warmer air can hold more water vapor than cooler air, so it doesn't rain out as easily. And so that increases the water vapor in the atmosphere. And we can actually measure this, okay? You can actually measure the increase in the humidity through time, and it's exactly the way it should be, okay? And that is a positive feedback, because the more water vapor there is, then the more greenhouse gas there is, so the higher the temperature is, which means the more water vapor there is. And that feedback is responsible for another 0.3 degrees from a watt per square meter of radiative forcing. So you get 1 watt per square meter from the direct effect, right? And that causes, from the direct effect, 0.3 degrees Celsius. You get a second 0.3 degrees from this water vapor feedback, causing the water vapor to go up in the atmosphere. A second positive feedback is called the Ice Albedo Feedback. The more it warms, the more ice melts in Greenland and Antarctica. The more ice melts in Greenland and Antarctica, the less reflective the surface is. And so the more radiation from the sun is absorbed and not reflected back immediately into space. Just like if you get into a car that's been sitting out in a parking lot in summer, it's much nicer to get into a white car than a black one. Black car just gets really hot, okay, because it absorbs everything. So when you melt the ice, it warms the temperature, which causes more radiation to be absorbed in the surface, which warms the temperature, which melts more ice. And that feedback is thought to add another 1/10 of a degree Celsius. Another positive feedback. The third big physical feedback is called the cloud albedo feedback. And the cloud albedo feedback is currently the one that's least understood. You see the uncertainties here? This one is 0.3 degrees plus or minus 0.6. This one is 0.1 degree plus or minus 0.03. And this one is 0.1 degree plus or minus 0.23. So we don't know if it's positive or negative. We don't know if this one is a positive feedback or a negative feedback. In either case, it's relatively small. So this uncertainty, it ranges from 0.1 to 0.3 positive feedback, which is dangerous. If it's negative about 0.1, okay? Which would cancel this one and leave you with that one and that one, okay? And so the cloud albedo feedback is more complicated because it turns out that warming changes the abundances of different kinds of clouds. And some clouds are more reflective than others, particularly clouds. If you've ever been to the coast of Peru, it's always hazy there, okay? Those are the clouds everybody's worried about, especially on the eastern tropical Pacific. It's a big deal. And so it's not quite clear, but the data indicates that this is mildly positive and not negative. But if it is negative, it doesn't change the story fundamentally. Thus, if you take the best guess, a doubling of pre-industrial CO2, 3.7 watts per square meter, means 0.3 plus 0.3 plus 0.1 plus 0.1, or about 0.8 per watt per square meter. Do the math, and you end up with a doubling of the pre-industrial CO2 concentration with that radiative forcing means about 3 degrees of warming. So the climate sensitivity is about 3 degrees of warming, all right? And that's because of, the lion's share of that is because of the positive feedbacks, not the direct effects, all right? Now, so you can calculate that directly from multi-hundred-year-old physics. But there's also other ways to calculate it. I'm sorry, there are other ways to calculate it, and there are other ways to measure it. And so everybody does this all the time. And you can look and see how the temperature changed in the past and reconstruct how radiative forcing changed in the past from geologic and other records. You can look at the impact of volcanic eruptions that put aerosols into the stratosphere and cool the planet. You can measure their impact on radiative forcing and see what it does to temperature, all right? Famously, the year without a summer, when, Tempura or whatever it was, the big volcano went off in the South Pacific. There was also Krakatoa was smaller. Krakatoa didn't cause the year without a summer, but it caused beautiful sunsets, okay? And so on. You can measure that and get an idea about what this radiative forcing is. You can look at glacial records and so on, and look at proxy data and rocks from years ago. And there's 6 different independent ways of doing this. And they all come out with the same number, about 3. 3 plus or minus 1 is about the way to think about it. 2 to 4 degrees is the climate sensitivity. And it has been for a long time. You'll read from time to time, if you start to pay attention to this area, that it, some study upends it, and it's always in the second decimal place. Okay, so that there was a study that was published in 2020 that said it was 2.6 to 4.1. It is true that the 2 degrees thing is starting to get less likely as we get up to 1.5 degrees ourselves, right? But nonetheless, this guy Sherwood and a whole bunch of others published a new range of 2.6 to 4.1, but that's, if you round, still very close to 2 to 4. The AR3 actually says the mean is now 2.85 or something instead of 3, right? Is what their guess is, but it's 3, right? Given the huge uncertainty, this is 2 to 4 degrees is still the way to think about this. And it's not as though it's relying on any one thing. All kinds of calculations, all kinds of measurements, all of them say the same thing. And the amount we've warmed so far, all right, would imply it's very unlikely to be a lot less than 3. Couldn't be 1 degree because we're more than 1 degree up already, all right? Now, how long does the 3 degrees of warming take from a doubling of the pre-industrial CO2? And I showed this in the first lecture. It takes quite a while, right? It takes millennia, right? And if you instantaneously were to do a doubling, you get about 50% of it from the really rapid warming of the continents, right? Warms the atmosphere, quantal from the sun loiter, they bounce into the earth, we all heat up, it stinks. But the oceans take a long time to warm up. So how do the oceans work? This I mentioned before. Remember I said in the first lecture, the drain of the world is right there. And it's because cold, salty water is more dense than warm, fresher water, okay? And so this is a place where the only place in the oceans where it's really cold, because it's far north, far south, you've got Antarctica, over here you've got the Bering Strait, and there's a big wide sea, and it's deep, it's 2 miles deep there. And so there the cold water goes into free fall, going down into the deep, and sets up this gigantic and complicated ribbon of water flow. And it also causes this North Atlantic drift and Gulf Stream along the surface. Red is along the surface, blue is way down deep. And this episode, since it stays on the surface all along here, it's evaporating all the time and becoming saltier and saltier. So that reinforces the drain of the world right there. Here's the important point. You know when you're canoeing down a stream and it's narrow and shallow, you're going fast, okay? You're going really fast. And as soon as you all of a sudden get into a broad, deep section, it slows way down. Well, the same is true here. The red stuff on the surface is actually only a couple hundred meters thick, right? And the stuff beneath it is 2 miles thick. The blue stuff is 2 miles thick. So the red is fast. Think of it as a year. It's a little longer than a year, but think of it as a year. And the blue is really slow. Blue is 1,000 years slow because it's so much thicker. And that's just canoeing, right? That's just water going down a stream. And so the point is that if you heat the surface up by doubling the radiative forcing, it heats the red up right away because it's right near the surface. But for the red to get down to the blue, it has to go up here and then sink down there. And then you get this like hot plume that is slowly for 1,000 years traveling along this thing. And it doesn't come up again to help warm the atmosphere for like 1,000 freaking years. And that's why there's this 1,000-year time scale also in the warming. And the bad news is that that's on top of the longevity of CO2 in the atmosphere. It's this long-term increasing impact of the CO2 on the temperature. So it keeps getting worse even after you've stopped it for 1,000 years or so. Okay, we are out of time, and I'll just finish the rest of this lecture next time and continue, okay? So download the next one, but I'm going to start with this one too, all right? See you guys. Stay safe and healthy.